When we talk about choosing appropriate summary statistics, the most important idea to understand is that no single summary works for every type of variable. Statistics are tools, and like any tool, they only work well when matched to the right situation. The usefulness of summary depends on two key features: the type of variable we are measuring and the shape of its distribution. If we ignore these features and blindly compute something like a mean or standard deviation, we may end up reporting numbers that are technically correct but practically meaningless. So before computing anything, we should always pause and ask, what kind of variable is this? And what does its distribution look like? That mindset helps ensure that our summaries are both mathematically appropriate and substantively honest. Let's begin with categorical and binary data. A categorical variable represents labels or group membership rather than numerical magnitude. For example, eye color, political party, favorite ice cream flavor, or type of vehicle. The key point is that these categories do not lie on a numerical scale. There is no meaningful sense in which one category is twice another, or in which you can add categories together. Because of that, arithmetic operations such as computing a mean or standard deviation simply do not make sense. If someone reported the average eye color in a class, we would immediately recognize that as nonsense. So the structure of the variable determines what kinds of summaries are valid. Instead of a means and standard deviations, categorical variables should be summarized using counts, proportions, and the mode. Counts tell us how many observations fall into each category. Proportions or percentages tell us what fraction of the total each category represents. And the mode tells us which category occurs most frequently. These summaries answer natural questions. How many? What fraction? Which occurs most often? They respect the fact that the data represent group membership rather than measurable quantities. By focusing on counts and proportions, we communicate the distribution of categories clearly without imposing artificial numerical structure. Consider a simple example: favorite ice cream flavors. Suppose we survey a group of people and record whether they prefer chocolate, vanilla, strawberry, or something else. A sensible summary would report how many respondents chose each flavor and what percentage of the total each represents. We might also report the most popular flavor as the mode, but reporting a mean flavor would be meaningless because flavors are not numbers on a scale. There is no logical interpretation of averaging chocolate and vanilla. This example illustrates a broader principle. The summary must align with the type of variable. Graphical displays for categorical data reinforce this idea. Bar charts and pie charts are built directly from counts or proportions. In a bar chart, the height of each bar corresponds to how many observations fall into each category. In a pie chart, each slice represents a proportion of the whole. These visualizations emphasize comparison across groups rather than numerical measurement. They remind us that categorical data are about classification, not arithmetic relationships. Now let's focus on binary variables, which are a special case of categorical variables. A binary variable has exactly two categories, such as yes and no, success and failure, pass and fail, or disease and no disease. Now, binary variables are extremely common in practice, especially when we are studying outcomes. For example, did a student pass an exam? Did a patient respond to a treatment? Even though binary variables are categorical, they have a unique property that makes them especially useful in statistics. It is common to code binary variables numerically using 1 for yes, or success, and 0 for no, or failure. And this coding does not turn the variable into a truly quantitative one, but it allows us to compute proportions conveniently. In fact, the mean of a 0-1 coded binary variable equals the proportion of observations coded as 1. That is a powerful and elegant result. When we compute the mean in this setting, we are not calculating an average magnitude. We are calculating a proportion. This gives the mean a very clear and interpretable meaning. For example, suppose 30 out of 100 students pass an exam. If we code pass as 1 and fail as 0, then the mean of this variable is 30 times 1 plus 70 times 0 divided by 100, which equals 0.30. That number is exactly the pass rate. So in this special context, the mean has a meaningful interpretation. It represents the proportion of successes. This dual interpretation is why binary variables are so important in statistics. They are fundamentally categorical, but their proportions can be analyzed with tools that resemble those for quantitative data. Next, let's consider ordinal data. Ordinal variables consist of categories that have a natural order, but the distances between categories are not known or not equal. A common example is a Likert scale. Strongly disagree, disagree, neutral agree, strongly agree. These categories clearly progress from low to high agreement. However, we do not know whether the distance from disagree to neutral is the same as from neutral to agree. The ordering conveys meaningful information, but it does not support precise numerical differences. Because the spacing between categories is undefined, arithmetic operations can be problematic. If we assign numbers 1 through 5 to a Likert scale and compute the mean, we are implicitly assuming equal spacing between categories. But that assumption may not reflect reality. Agree may be higher than neutral, but we cannot guarantee that the step size is identical at each level. Therefore, computing a mean can create an illusion of precision that the data do not truly support. This is why we must be cautious when treating ordinal data as if they were fully quantitative. A safer approach for ordinal data is to report the mode and the full distribution of responses. The mode tells us the most common category. Reporting counts or percentages for each category preserves the ordering without imposing questionable numerical assumptions. Bar charts are particularly effective here because they display how responses are spread across the ordered categories. In some contexts, the median may also be appropriate, since it depends only on order and not on numerical distance. But even then, interpretation should remain tied to the category, labels themselves rather than numerical values. Now we turn to quantitative data. Unlike categorical or ordinal variables, quantitative variables are fully numerical and support a wide range of mathematical summaries. However, even here, not all summaries are equally informative in every situation. The choice between mean and median, or between standard deviation and interquartile range, depends critically on the shape of the distribution and the presence of outliers. Before summarizing quantitative data, we should always examine the distribution using a histogram, dot plot, or box plot. That visual inspection guides our choice of summary statistics. When a distribution is approximately symmetric and does not contain extreme values, the mean and standard deviation provide an efficient and interpretable summary. The mean captures the balance point of the distribution and represents a natural notion of a typical value. The standard deviation describes the typical distance of observations from the mean. In symmetric distributions without outliers, the mean and median are usually close to each other, and no single observation dominates the summary. In this setting, mean and standard deviation are both meaningful and appropriate. However, when a distribution is skewed or contains outliers, non-resistant measures like the mean and standard deviation can be misleading. A few extreme values may pull the mean far away from where most observations lie and inflate the standard deviation. In these cases, resistant summaries are preferred. The median provides a stable description of a typical value because it depends only on order, not magnitude. The interquartile range, defined as Q3 minus Q1, summarizes variability in the middle 50% of the data and is not affected by extreme observations. A trimmed mean can offer a compromise by removing the most extreme values before averaging. Quantitative count data, such as the number of doctor visits, emails received per day, or customer complaints, often occupy a middle ground. While counts are numerical and support means, they are frequently skewed with many small values and a few large ones. For count data, it is especially important to examine the distribution shape before choosing summaries. Relying solely on the mean can hide important features of skewness. Reporting the median and interquartile range alongside or instead of the mean often provides a clearer and more honest picture. The guiding principle for quantitative data is straightforward. If the data are symmetric and well-behaved, use the mean and standard deviation. If the data are skewed or contain outliers, use the median and interquartile range, or possibly a trimmed mean. There is no one-size-fits-all summary. Choosing statistics that align with the distribution ensures that our reported numbers genuinely reflect the underlying data rather than distorting them. Good statistical practice is not about computing as many numbers as possible. It is about choosing the right numbers. Now let's bring all of this together in an example comparing three small data sets: incomes, test scores, and Likert ratings. The income data include a high value of $120,000, making the distribution right skewed. The test scores are tightly clustered and approximately symmetric. The Likert ratings represent ordinal responses on a 1 to 5 scale. When we compute summary statistics, we see different patterns emerge. The mean income is much higher than the median because the high outlier pulls it upward. For test scores, the mean and median are very similar, reflecting symmetry. For Likert ratings, the most meaningful summary is the mode and the distribution of responses rather than the mean. This example highlights the central lesson of this section. The choice of summary statistic must match the type and shape of the data.